everyone, this is Varun. Welcome to Aerospace Structures. Today we are going to discuss about the energy methods which we use in structural engineering or aerospace structures. Okay, let us collect our previous concept. We have two concepts here. One is the elastic method and next is the virtual work method. I am not going to discuss what these two are. Just I am refreshing the concept which everyone knows. In elastic method, the stress or displacement are calculated by employing the equation of equilibrium and compactability. That is, by using the equation of equilibrium and compactability conditions, what we deduce by applying this elastic method is the stress or displacements. And next what we have is that the virtual work method, which relies on the principle of superposition, and this is helpful in calculating the force, reaction and displacement in a structural system. And finally what we have is that the energy method. This is one of the alternate method and which is more powerful than these two. And when we have a complex structure, if we need to find the displacements and reactions, we use these energy methods. And moreover, the advantage of energy methods is, first, it provides an exact solution to many of the problems, and second, rapid approximation. When you compare other methods, this energy methods has given a rapid approximate solution to many of the structural engineering problems. And the second thing is, it has also provided the solution for statistically indeterminate beam. And finally, it's a simple solution to deflection problem. In energy methods, we have the two concepts. One is the total potential energy and another is total complementary energy. Okay, now let us take a bar which is hinged to one point, or which is fixed to one point. And now what we do is that we apply a load P on this rod. As a result, we have a deflection of Y. Now, when we draw a load versus deflection curve, deflection versus load, that is the deflection on x-axis and load on y-axis. For a non-linear system of load deflection, what we get a curve is a power function curve, which is given by the following. And moreover, when you look into the curve, what you observe is that you have a strain energy U and complementary energy U. And moreover, the load has been increased, the deflection has been increased from 0 to Y, as the load has been increased from 0 to P. If we increase a load by delta P, we get a deflection by amount of delta Y. And this is the load versus the deflection curve for a non-linear system. Okay, now once again the same picture, the strain energy. And I would like to recollect here, one thing I would like to recollect here, when we apply a load, the work is done on a system, and by the principle of conservation of energy, then energy is neither created nor destroyed, but it can be converted. Here, what happened when a work is done on the elastic rod? That is, when we apply a load, there is a deflection. That is, a work is done, and this work is stored within a body called as the strain energy. The expression for the strain energy is given by U equal to integral 0 to Y P dy. This is the case when you draw this load deflection curve. That is, the strain energy from 0 to Y. That is, when an element or when a rod is extending from 0 to Y, the amount of strain energy which is stored in a body is given by integral 0 to Y P dy, where P is the applied load and dy is a small elemental increment. And finally, when you look into the curve, the area OBD gives the strain energy, and ultimately the area OBA gives the complementary energy. The term complementary energy is new to you, and moreover the complementary energy is given by C equal to under root 0 to C equal to integral 0 to P by T. Okay, let us discuss what this exactly the complementary energy. Practically speaking, till now there is no physical interpretation or there is no physical meaning for this complementary energy or the complementary function, but it has some mathematical significance which can simplify our structural problem. Purely it is a convenient mathematical quantity, and moreover the most important thing is that this complementary energy also obeys the principle energy conservation of energy, and moreover the strain energy U is given as integral 0 to P. That is our when we take a rod and when we apply a load P, it has been extended towards a length of Y. And what we can deduce that U equal to the strain energy of a system under that is P integral 0 to Y P dy. When you partial differentiate with respect to Y, that is deflection, what we get is the magnitude of load P. And let us look into the a complementary energy C equal to under integral 0 to P Y dP, and when we partial differentiate this complementary energy with respect to P, what we get is deflection. This is the important. If we need to find the deflections, then we need to have a complementary energy. But if you need to have a load, to determine a load on a given structural complex system, then what we need to do is that we need to formulate strain energy. Now, since we are discussing about the nonlinear system, and it can be written as the load versus deflection curve for a nonlinear system can be written as P equal to by to the power of n. Here B and n are the constant, and the strain energy and complementary energy for this function is given as U equal to integral 0 to Y P dy. When you substitute this value of P in the following equation, what we get is 1 by n integral 0 to P by B whole to the power of 1 by n dy. And similarly, the complementary energy C equal to 0 to P Y dP equal to n integral 0 to Y by to the power of n dy. Here we have for nonlinear system of load deflection curve, the strain energy and complementary energy. And what if it is a linear system? Then the load versus deflection curve is a straight line. Finally, what we have is dou U by dou Y equal to P and dou C by dou P equal to Y by N. Sorry, this is for non-linear system. And for a case of linear elastic member, that is the load versus deflection curve is a linear, and we can represent it as follows. And the triangular area of OBD gives the strain energy, and the triangular area of OBA gives the complementary energy. Finally, what we get is when we partial differentiate the complementary energy with respect to load, what we get is a deflection Y. And when we differentiate the for a non-linear system, what we get is the following relation, that is dou C by dou P equal to B n Y to the power of n equal to n times the loads. And for linear case, n equal to 1. And finally, what we can say is that du by dy, which is equal to dc by dy equal to P, and du by dP equal to dc by dP equal to Y. That is, the strain energy and complementary energy can be interchanged. Thank you very much. This is Varun signing off.
Like, share and subscribe. hit the bell icon for more updates.